You will recall the one sample proportion problem had a p hat with the number of successes over the number of attempts. So it might be something like 14 out of the 37 people did whatever it is. And we could construct a confidence interval off of that that looked like this: p hat plus or minus a critical value times the square root of p hat 1 minus p hat over n. And this z star here was related to the confidence level I wanted. So if I wanted a confidence level of, say, 95%, I would use a z star of 1.960. Well, in the next unit, we want to have two sample problems. So I want to have a p hat, say, for the boys, and a different p hat for the girls. And to help keep that separate, I would call this p hat 1 and p hat 2. And what I want to do is come up with a confidence interval for the difference in two proportions, for how different these two values are, this p1 and p2. Now, just like before, we have three conditions that have to be met. I need a random sample. I need to check for normality. And I need to check for independence. The random sample ideally is an SRS, or something we can consider an SRS. Normality is achieved with large counts, which for a proportion problem means 10 successes or 10 failures. And for independence, when I sample from a finite population without replacement, I talk about the 10% rule, where the population needs to be at least 10 times bigger than the sample. Beyond that, the format looks kind of similar to what we had before. We'll have the estimate plus or minus a critical value times the standard error. And so the estimate is p hat 1 minus p hat 2, or put a different way, how different are, say, the girls and the boys. The critical value is just like before, the z star critical value. And now we have to worry about the standard error. You might recall from a previous chapter when I wanted to find, say, the variance of x minus y, that was simply the variance of x plus the variance of y, provided that my two samples were independent. So let's see how that would apply to this problem. Now, the standard deviation for the first p hat is p hat 1, 1 minus p hat 1, over n1. There's the first standard error. Now, the second standard error is p hat 2, 1 minus p hat 2 over n2, and I've got the square root of that. Now, I can only add these things together if I'm looking at the variance. So when I get this addition going right here, I've actually got to square both of these things. But I'm not interested in the combined variance. I'm interested in the combined standard error. So then I need to take the square root of all of that. Now, that looks pretty awful right now, but it's actually not near as bad as it looks. So I want to clean this up just a little bit. I notice that this square and this square root will end up canceling each other out. Likewise, on the portion to the right, whoop, not that, over here on the right, this square root and this square will cancel out. And I end up with a much simpler formula. So this whole thing under this radical is the standard error of the difference in the two proportions. So that actually is what goes right there in the formula. So this part that I'm going to highlight is the formula for the confidence interval for the difference in two proportions. P hat 1 minus P hat 2 plus or minus the critical value, C star, times the square root of P hat 1 times 1 minus P hat 1 over N1 plus P hat 2 times 1 minus P hat 2 over N2. This formula will work. This will give me a good confidence interval, provided that the three conditions we talked about before are met for both groups. Those things have to be met for each group, and then also the two groups must be independent. If that's met, those three conditions for both samples, and then that condition in black, considering the samples together, if those are met, then this formula right here is a good formula for a confidence interval. In the next video, I'll work a couple of examples to show you how this would actually play out.